Okay, guys, I think we can get started. So today is my great pleasure to host Dr. Engin Kirda from the Northeastern University. He is a well-known and well-established researcher in our cybersecurity community. So 10 years ago, when I was a graduate student like you, I read a lot of his papers. And right now, I'm an assistant professor. I still need to read a lot of his papers. So Dr. Engin is a professor of computer science at Northeastern University. He has co-founded the Secure System Lab that across 5 institutions in Europe and United States. His research interests focus on the malware analysis, detection, web security, and social network security. He has also co-founded a company which was acquired by William Well. He has also served as the program chair for many top-tier cybersecurity conferences such as NDSS, CCS, Usenet Security. So some of you probably have no idea of those conferences. Typically, if my students can publish one CCS paper, I'll let them get graduated. Okay, so without further ado, I'll let Dr. Engin to start his talk.
Thank you very much for the kind introduction. I guess I can just say good morning, everybody. Thanks for coming to this talk. It's a pleasure to be here and to also check out your beautiful campus. So my talk today will be on work that we published a couple of years ago, but there's follow-up work that has been appearing in some of the other conferences. It's a relatively simple issue, but that can have big impact. That's why I've given this talk a few times, so I thought it might actually be interesting for you. So the talk will be on a system we built called T-Reqs, and I'll be talking about this problem called HTTP request smuggling, and a technique we actually used to detect these things automatically, and some evaluation we also performed, and did some measurements on the internet. So my background, so I moved to Northeastern in about 10 years ago, in fact there. Before that, I was faculty in Europe. I spent a lot of time at the Technical University of Vienna. Then I spent some time at Institut Eurocom in France. Then I moved to the US. So right now, it's about 50-50. So half of my time as faculty I've spent in Europe, half of it has been in the US. So I'm typically active in system security. So I try to secure systems of all sorts. I've done quite a bit of work on malware detection, malware analysis, which is still a huge problem since about 2004. And web security has been an area I've been interested in since mid-2000. So that's an area where I've published quite a bit. And this is so this talk is actually on web security. It's like a sub-issue in web security. It's something we've been seeing quite a bit relatively recently. In general, though, I'm interested in all practical security problems except very theoretical stuff. So I don't have the background to attack those issues, but if it's systems, if it's actually practical, then it becomes interesting. So my talk today, I could have talked about something general. Sometimes, that can be very useful, or something, presenting something specific. So for example, I thought, it's actually interesting to look at web security when I started doing it and where we are today, to sort of compare the differences, right? That could have been something. I could have spoken about maybe, my one-time experience in taking a technology that you develop at a university and transferring it to industry, doing a spin-off company, that has been sort of interesting. But I actually thought that this specific CCS paper that has been quite impactful is something I'm really interested in. Some of my students are interested in. So it's an interesting real-world problem. So I thought I'll talk about that today. So the work I'm presenting today was led by my PhD student, Behruz, who graduated, so he's not my PhD student anymore. So my former PhD student, and Steve, who's close to finishing. So they actually led this work. It was co-led by my former student, Kaan Onarlıoğlu from Akamai. So he's been working at Akamai for quite a while. So Kaan's contributions to this work were actually essential. He's the CDN expert. So he helped us out a lot with respect to understanding some of these issues. It's very instrumental. And I basically was lucky enough to work with these very smart people, right? So I'm basically presenting their work. So they led most of the work, and I was lucky to be involved in this work. So So the talk actually I'm giving today, if you're really interested in reading the technical details, there's a paper at ACM-CCS from 2001. So the paper is called T-Reqs, HTTP request smuggling with differential fuzzing, like the title of this talk. So all the technical details, all the results that I'll be presenting today are in the paper as well. So if there's something unclear, the paper's online, you can download it. Feel free to ask me questions. If I can't answer them, I can forward you to the real experts who can actually answer. So what is HTTP request smuggling, right? So why is this problem kind of interesting? So historically speaking, HTTP request smuggling is not a new issue, right? It's a problem that has been around since about 2005, I would say. When I first heard about it back then, I was teaching security. I thought, hey, it would be interesting to have a couple of slides on this problem. It's like a smaller issue, and I can include that as a part of my class, right? So I've done that. Back in 2005, I was talking about this issue. It was not as widely known as today, and it was less impactful than it was today, right? So the question is, what really changed since then, right? So it was discovered back then, but it started gaining attention a few years ago. So around 2019, James Kettle gave a black hat talk, and he presented a lot of issues with modern websites today where HTTP smuggling, this problem that I'll be explaining, was detected. And he showed that, hey, this can actually lead to a lot of big, important, bad problems, right? So although the problem it was actually old, thanks to the landscape of the internet today, how things have evolved, the fact that we have all these CDNs today, we have companies like Akamai serving a lot of the web pages on the internet, the problem became more relevant pretty much. So lately, the focus for this issue has been focused on transfer encoding versus transfer length discrepancies that I'll be demonstrating to you in just a bit. So the focus had been on that. So people showed, if there are certain headers that you are playing around with, that can lead to some problems on servers. That was the focus, but we thought, hey, is this actually a more generic problem? Is this actually a huge, much larger problem than what was being reported? So that's why we started looking into this. And since then, we've had a couple of works specifically focusing on these discrepancy on these smuggling issues. So if you're wondering, okay, what's the impact of this specific vulnerability? If you actually check bug bounties, you are actually going to see that HTTP request smuggling is appearing more and more. So people are actually discovering these in real websites, they're reporting them, and they're actually making money by getting bug bounties. So if you actually talk to people working at Akamai once in a while, they're going to tell you, yeah, we just got this report yesterday, and there's somebody found this smuggling issue on some important website, we're trying to fix it, right? So this is something that is appearing more and more. They were hearing less of this issue, say 10 years ago, right? And years ago, I used to think, well, maybe it's not that interesting, small issue, but now it became much more relevant. Okay, so what is this issue, right? So if you're actually surfing around on the internet, right? So DuckDuckGo is my favorite search engine. So, and you're typing something, right? Suppose you type in funny cats and you're looking for that, right? So what would happen in the background? Your browser would take this request, obviously, right? It would send it to a remote server, and it might actually end up sending a request like this. And the request would look like, get HTTP 1.1, there's some headers, and you say content length is 16. So that's one way of formatting this request, sending it to the foreign server, right? So in this case, content length is 16 because I'm taking this query, which is equal to funny cats. So the length of that body is 16 characters. So I'm basically telling the server, interpret this message, parse it accordingly, and then, send me back the results, right? So that's one way of representing it. So this is the request line. These are the headers, and this is the request body, right? So this is one way of representing this. Another way of representing this, the same request, depending on your implementation choice, depending on how you like to deal with, implementing the HTTP specifications, could be, instead of saying content length, you could say, I'm going to use transfer encoding, which is another way of representing this. You could say chunked encoding, and then you're basically saying, you're defining different chunks, and you're also saying how long these chunks are. So the server receives this, it sees from the headers that this is actually chunked encoding. So it would actually interpret this accordingly. So I could say, query has 6 characters. It reads it. Then it looks at funny cat. It looks at hexadecimal A. It takes this many A's. What is A actually? It's like A 10, right? Exactly. So it says 10 characters, right? It would take that. And then 0 basically indicates I'm at the end of this body, right? So this is one other way of actually presenting. So content length versus the chunk encoding. So these requests are, in terms of context, they're identical. So the question people started asking is, all right, so I have 2 different implementations or 2 different ways of interpreting this request. What would happen if I send one request and I say transfer encoding is chunked? At the same time, I say content length is 16, right? This is not actually a valid request. So I'm actually mixing both of them, right? I'm supposed to use one header, but I end up using both of these headers at the same time, right? So what would happen? So it turns out the way such a request is handled really depends on the implementation of the server, right? If you have Apache, maybe it deals with this in a certain way. If you have Squid, which is an open source proxy, maybe it decides to deal with this in a different way. So if you say transfer encoding is chunked and you say content length is 64, and you attach a bunch of A's, right, at the end of this request, how the server deals with this really depends on how it's actually being implemented. So the issue today is that often you're not directly reaching a remote server. You're actually reaching this remote server through other servers, right? Because you have content distribution networks. So you might have a company like Cloudflare or Akamai, which receives the request, right? So you receive the request, you interpret it, and you forward it to the destination, right? So Akamai might take your request to Apple, it might interpret it, and it forwards this request to the Apple server. So it's actually in front of the Apple service, right? So you have a reverse proxy, and you typically have the origin where you forward these requests. So if this request is taken by the reverse proxy, say the Cloudflare servers, or say the Akamai servers, it looks at this, and it might actually interpret this very differently. And it might say, based on its implementation, it ignores the transfer encoding. It says, I'm going to take a look at the content length. It says it sees it's actually 64. So it would take this entire request here, including the AAAs, right? And it was forwarded to the origin, right? So it takes it and sends it to the origin. The origin receives it. Now the origin is actually looking at the same request, but because it's been implemented differently, it might ignore the content length. It might decide to actually take a look at the transfer encoding, which is chunk, right? So in this case, you have one request being forwarded and being interpreted very differently, right? So it might actually take a look at this. It ends up ignoring the first part because it's actually looking at this as chunk encoding. And it might just see a request that has a bunch of A's, right, as the request itself, which is not a valid request, right? So in this case, where nothing really bad happened yet, you're sending a request, the origin interprets it and sees that it's actually an invalid request because it sees a bunch of A's, or it sees the content, which is AAA. It's not a well-formed HTML, right? So you basically manage to inject some information that is being forwarded from one server to another, right? So this, if you think about this, might sound like not a big problem. Okay, so what, right? Maybe the server crashes, maybe it's not valid HTML, nothing really potentially bad happens yet, right? So you have a bunch of A's here. So the problem is that you have a bunch of A's, but you're sending everything on the same connection. Typically, the reverse proxy establishes a connection to the origin, and all the requests are sent over the same connection. So it's basically like a queue, right? So if there's another request that actually comes later, where you're looking for dogs, right? Now you end up having these 2 basically requests, and one of them becomes an invalid request. So you have a bunch of A's, then you have a valid request, but the origin is going to look at the A's and it's going to generate an error message, right? So what you successfully managed to do right now is to inject some extra packets, and you manage to create confusion, right? So the origin is seeing a request that's actually not a valid request, so because there are a bunch of A's, right? Instead of a bunch of A's though, I can actually inject a valid request. So just typing instead of typing random characters, what if I say get ABC HTTP 1.1 and maybe I send this request to Google, right? So I'm sending a valid request to Google. So what you can do in the simplest case is by injecting these extra packets and creating some confusion, you are actually creating a discrepancy between requests, right? So maybe I'm asking for Google, and the origin server maybe sends me a different page, right? So I'm asking for a very specific login page, but because I brought this entire thing into desynchronization, I end up seeing other pages, right? So that's one thing that can actually happen, right? So people have actually looked at this and they said, okay, the fact that I can smuggle these requests, that I can inject these extra packets, what does that mean, right? So they've actually found out that you can have response queue poisoning. Like I said, I'm looking for a very specific page, I request it, but because extra packets are injected, the servers are desynchronized and I start seeing other pages, right? If I go to CNN.com, maybe I end up seeing pages from BBC.com, right? Because I'm injecting extra packets. So that could be one potential issue, right? So I have an extra, basically, packet that I've injected. So all the mappings sort of, the queue is basically poisoned, right? So people have shown that you can do this to poison web caches, right? So, you have different people requesting different pages. And I have, say, Squid that caches some of these pages. And, if I'm injecting this extra packet, right, the mapping changes. Like I said, so that will be not a good thing, right? So everyone who's going to CNN.com, I can trick them into going into attacker.com, right? And I can start doing things like that. People have also demonstrated that you can potentially bypass security controls, right? What if I have a firewall and that firewall is looking for very specific headers? The fact that I'm able to put these headers and smuggle them means that maybe that server is not going to see these malicious headers and it's not going to be able to block them, right? So if I have this thing that I'm actually smuggling in, it ends up being forwarded, although Squid or Apache should have seen it, right? Or Akamai should have seen it, right? So people have demonstrated using bug bounties and attacks that, yeah, you can do a bunch of things. And smuggling is maybe a relatively simple issue, but it can actually lead to quite a bit of damage, right? So it's actually taken quite seriously these days. So in fact, there was a Slack case for Slack where it was March 2020. They paid out more than $6,000 of bug bounty because somebody actually figured out how to smuggle packets and how to bypass Slack's controls, right? So Slack was looking at headers. The fact that you can smuggle these requests basically means that you could bypass their security. So by using HTTP request smuggling, you can do a bunch of these things. So the first summary is that discrepancies in body parsing behavior of servers can be used for HRS, right? HTTP request smuggling. And that can pave the way for a number of attacks, right? So sounds trivial. Yes, you're actually injecting these extra packets, but yeah, it can actually lead to real world security implications, security problems. So here are the research questions we wanted to actually explore, right? So first, can you actually detect these types of attacks systematically? Can you actually build tools to scan websites and figure these things out, right? Because, a lot of the cases, James Kettle was doing these things by hand, manually, but we wanted to actually automate the process and find as many bugs as possible, right? Using some automated technique. Another question was, okay, what technology stacks are at risk, right? Is Akamai more at risk than, say, Apache, or is Squid more at risk because, of these discrepancies, right? So what technology combinations are pretty risky, right? Combining Apache with Squid, is that actually a bad thing? So we wanted to measure that and we wanted to understand that. So another question was, what parts of a request can induce body parsing discrepancies? So the question there was, yes, you can play around with the content length and the transfer encoding, but are there other things you can do, say with the request body, and you can start combining them, that can lead to even more issues, right? Is it just restricted to these two headers, or are we talking about more things in the request that can actually lead to problems? Another question was, what escalates a body parsing discrepancies to HRS, right? Just because two servers have been implemented differently, does that mean that, yeah, automatically you're going to have some sort of a HTTP request smuggling vulnerability, or do you need some preconditions that need to be fulfilled before some discrepancy actually leads to an issue like that. That's also something we want to understand.
Question.
Yeah.
Should the body parsing be addressed as a software engineering specification issue because you have conflicting header lines?
It has to do with the specifications. We'll get to that in a bit.
Okay.
You're right. It has to do, so if you're asking, okay, why is this an issue? It's because some of the protocols we're dealing with, specifications are very complex, right? And HTTP leaves some room for interpretation, right? It's very difficult to define everything you're supposed to do if there's an error. And it often, because they can write down everything, they leave you some room for interpretation. So it doesn't mean that the way Apache has been implemented is wrong. It's just something we haven't thought about, right? The fact that Apache might implement it a little differently than, say, Squid. And that combination leads to this problem.
Okay, then if we go back to HTTP 1.0,
yeah,
it's non-persistent.
Yeah.
So the TCP tear down after every request. So there's no way you can smuggle.
Right. So if you're using 1.0, there might be cases where it might be possible, but yes, like this queue poisoning stuff you'll see is more difficult, of course, because the connection breaks, right? Exactly. But then you get into performance issues. That's why. Right. So that would be a potential solution, but you need that connection for efficiency. That's why.
Then the last question is that we teach students saying HTTP is stateless. So how come that AAAs could stay in the queue or buffer?
Because of HTTP 1.1, because you can establish a connection. So the protocol itself is stateless. The server needs to maintain state by taking your cookie information and tying it to some identity, but you can have persistent connection. So if you're actually establishing a connection to a server, say Google, using 1.1, you'll see that the socket connection will not break. So I can just pipe and send as many requests as I want.
So in that case, HTTP 1.1 will not, even though the TCP connection is there, but you will not cut it and flush it, like clear its own state until
the state completely depends on the implementation of the server. So the application will need to maintain state with sessions. So the first part was, okay, can we systematically test for HRS, and then what technology stacks are at risk? So of course we have to think about ethics as well. Well, first, availability. So T-Reqs is open source. You can actually access it if you like to use it. It's available on our on the lead authors' websites. So it's downloadable, and people have downloaded it. They've been using it, so we're happy about that. There were some ethical considerations as well. So doing a study like this, where you're injecting packets, performing some experiments, you need to do it in a more controlled environment. So you can't just randomly, connect to companies and start attacking them. That doesn't work. So we did not launch any attacks against external entities. We performed responsible disclosure. So every time we identified an issue, we reached out to these companies. We spent several months, emailing them, telling them how to fix things, and we still continue to do that. And we also sent a copy of the paper and data to all affected parties, right? So if you found something, say in Cloudflare, we actually did contact them. We sent them a copy of the paper. We asked for feedback. So we try to follow everything and do everything ethically. So one idea we had was, okay, can we actually use differential fuzzing to detect this type of stuff? And it hadn't been done with respect to web requests like this. So fuzzing is a well-established software testing approach. Differential fuzzing aims to determine different behaviors when you're actually giving something the same input, right? Something that people have been using in software engineering. So we thought, hey, this could actually be suitable for our purposes because people used it in the past to find issues in protocols like TLS, right? They were using differential fuzzing. So the idea here was, okay, we have different implementations. Can we actually feed them the same input and just figure out how they behave and then start comparing these behaviors? So we thought this would actually be suitable for our purposes, right? Because people have also used it, as I said, for TLS, side channel identification and things like that, but not necessarily in this space. So T-Reqs as a first, initially generates inputs. We know how the requests are actually constructed, right? So we have, the header information. We have a specification language, right? A grammar for this. So you know that it has to start with a method, a URI, a protocol, and a version, right? So we know all these things. We know that the method can be get, post. It could be trace, right? Which is useless. Then we have a URI, right? So we know exactly how this header part is actually constructed. We have a protocol specification here as well. We have different versions, etc. So because we know exactly how this is specified, this means that we can use this language, these grammars to generate, starting from one input, we can generate a lot of different inputs automatically, and then we can feed it to the application to try to figure out how it actually reacts to this, right? So this is one part, right? So we can actually mutate inputs, right? So if there's a trace /abc http1.o, for example, right? We can do string mutations. So we can take any of these strings, we can mutate them, we can integrate different bugs, right? So I can insert a slash and then see how that server reacts to it, right? I'm basically generating bugs, right? Or non-valid requests, or a question mark, and then see how it actually reacts. I can also do tree mutations, meaning I can, maybe leave out certain words or like insert different words here, right? So instead of trace, I can write HTTP, or I can, maybe write HT and then see how the server reacts to it, right? So I can generate lots of these packets. So we thought, okay, now we have this, system that generates all these random inputs starting from some seeds. We set up an experiment. So the idea here is you have an input grammar, as we saw. You generate lots of inputs, right? You feed these inputs by, you mutate them and you feed them into a specific target application, right? A server and an origin pair, right? A proxy and origin pair. You send requests to them, and then you look at the reactions, right? So if I'm sending a request to say Apache, what does it do with it, right? What kind of a message it actually generates, right? So we looked at Apache, Nginx, Apache Tomcat, HA proxy, so a bunch of popular technologies, right? And we wanted to figure out, okay, if I'm sending a mutated packet like that, what response do they generate, right? How do they actually react to that? And we took the responses, we're looking at the requests they're actually forwarding, they forward these requests to us, and we write them in a database, right? So the first step was just to collect a lot of information. You generate inputs, you feed these inputs into these technologies, you look at if a packet is actually, an error message is generated, or if it actually forwards it. If it forwards it, how does it actually, what does it forward, right? What part of the request does it forward? Does it forward everything? Does it modify it a bit? And we actually put everything in a database, right? So the first part is you've stored all these requests, right? Thousands of requests, everything is in the database. Now, the cool thing is, because you have all this information, now you can start comparing how these different technologies dealt with it, right? How did Squid deal with it? How did Apache deal with it, right? Did they actually forward the same exact request, or did they forward it with little variations, right? That's what we wanted to actually find out. The second summary is T-Reqs, the fuzzer, and the experimental setup let us systematically analyze the body parts and behavior of servers, right? So in this very controlled environment, you generate lots of inputs and you look at how these servers are able to deal with these requests actually. So the second part, the question was, okay, so what parts of a request can induce body parsing discrepancy, right? So, we looked at, that's something we wanted to understand as well, right? So we wanted to figure out, okay, can you play around with the request line, right? We know we can. How about request headers, right? Is that something that we can automatically modify? What about the request body, right? People hadn't looked at the request body, but can you actually do something in the request body that might result in some potential problems? That's something we wanted to understand as well, right? So with the request body, we did a bunch of experiments, right? So we came up with different tests, right? Specifically modifying these inputs for the request body. And then we started comparing technologies against each other, right? So you have this large database where you see how these packets are being forwarded by doing different tests. And now you can start comparing them, right? So we had in the paper, you'll see the detailed description of these tests, but mangled method is a specific input where the method has been modified a bit, right? For example, distorted protocol is instead of HTTP, maybe we add a slash to it or like a question mark, or all these tests were very specific tests. And for these specific tests, we're looking at how the different technologies responded to them, right? Are there differences? So if you start comparing the technologies we looked at against each other, you will actually end up seeing, for example, that Squid and HA proxy for these very specific tests had differences, right? They had discrepancies. And we did this for all the technologies. So now you actually have a possibility of comparing different technologies against each other for these different different tests, right? So for example, you can look up your database, you can find out for this very specific request, Squid deals with it very differently than say HA-proxy, right? So for example, this sort of protocol is instead of an H, we add a P there, right? And then we see how these technologies react to it. Mangle method is, you put a dot, for example, right? All these small issues that were generated automatically. Or instead of 1.0, we put like a 0.9, right? And see what actually that leads to, right? Or you do multiple mutations in the same request, right? So all of these things are done automatically. So if you look at the overall results, no need to go into them, but what that graph demonstrates is that, yeah, for all these technologies, right, popular technologies, we saw a lot of differences in the way they were interpreting these errors, right? So all the errors that we were generating automatically, they did not deal with the errors in the same way, right? They forwarded these packets, although there were errors in these packets, and the way they did this for different technologies, there were a bunch of differences. So we did the same thing for the request headers. For example, what would happen if you say transfer encoding is identity and chunked at the same time, or you put random values, right? So different tests. For the headers, you also see that these technologies show a lot of differences for the different tests that we actually were performing, right? What this indicates is that different technology combinations do result in different behaviors, right? At quite a large scale. Right? We did the same thing for the request body, right? So we looking at that, for example, a classic one is the chunk data termination. So at the end, what would happen if you don't put a /r/n, right? Which according to specification, you should provide it. But if you leave it out, right? So the chunk data termination is different. How do different servers react to it, right? So for this, we had specific access to how Akamai was actually, dealing with these requests. That's why, specifically showing you the Akamai results. Yeah, all these tests that we performed for the request body actually also resulted in discrepancy, right? Which is something people had not looked at in detail back then. But this graph demonstrates to you, a lot of these tests, yeah, they do show the differences, right, for different technologies. Okay, so what does that all mean, right? So summary is mutations in all parts of the HTTP request, the request line, headers, and body can actually cause discrepancies between servers. Until this paper, people had looked at the request line, right, or like the request headers. But basically, they had looked at the request header, and they showed that, yeah, that can lead to HTTP smuggling, but we actually performed larger tests just to demonstrate that this is actually in all parts of the HTTP request, not just the header, right? You can come up with a lot of tricks, a lot of implementation differences, not just one where one header is provided, two headers are provided that have conflicting meanings pretty much. So the question now is, yes, you have these technologies, and when you compare them, they lead to different implementations, but that doesn't necessarily mean that this is going to automatically result in an HTTP request smuggling problem, right? It just means that, yeah, they've been implemented differently, but you haven't really shown that this can lead to real world problems, right? That's the missing link. So the final question we wanted to answer was, okay, what actually escalates a body parsing discrepancy? All these graphs I showed, yeah, Squid compared to Apache looks different, right? They deal differently with the same input, but does that mean that it's actually going to lead to an HRS problem, right? So we wanted to test for HRS. So we used a technique inspired by previous research, right? So we put each pair in a proxy origin setting. We sent a smuggler request, right? And we sent a benign request right after that. And we look for an error response from the origin server, right? So basically, you're injecting these AAAs, and you're trying to see the error message and see if you were able to actually inject a packet that was not valid, right? So the server actually creates an error message, right? So by doing this test, we confirm some HRS, right? So looking at, for example, Akamai versus, say, let's see, it's Apache, that combination by doing this trick where we injecting the AAs looking for error messages, allowed us to confirm some, real world HRS issues, right? So you're able to smuggle a packet and it's actually forwarded all the way to the origin, right? Which is something that shouldn't happen, but it did. So we did confirm some HRS problems for some combinations, just to make the point that yes, some of these discrepancies can indeed lead to this real world problem, right? So here are more results, for different server combinations where we were able to actually confirm manually that yes, these are actually leading to real world problems. Again, we had more access to Akamai. That's why if you just look at Akamai with different technologies, you see that for a lot of the technologies out there in our list, we were able to confirm an HRS issue, right? Which means that not just one combination, but many of these combinations are potentially going to lead to this smuggling issue, right? Which means that the problem is pretty large, right? So body parsing discrepancies on popular servers are opening the door to HRS, right? So what are the failure conditions? So by, while confirming these HRS issues, we also wanted to find out, are there cases where HRS actually doesn't work, right? When does it actually fail? So in some cases, the mutation is not preserved, right? So some server implementations, I believe, if I'm not wrong, it's like Amazon, they do modify certain things, maybe on purpose, maybe not on purpose, but the mutation is not preserved, right? So basically when it goes to the origin server, the attack fails, right? Because the mutation has been modified. So that's one very common failure condition. Another one is the connection is closed, right? Maybe on purpose, maybe by luck, sometimes you send the request, right? This request is actually passed on, but the origin server basically just breaks the connection. Maybe because they detect something, or maybe the error message causes the connection to be killed. In that case, you can't send more packets, meaning that attack does not work. Or sometimes the exit point simply cleans it, right? So the packet is received there, the attack reaches the exit point, but at that point they might do some sort of cleaning up, and then the attack fails, right? So in the paper, these failure conditions are also described. So the attacks that we tried out were not always successful, but we did manage to find a number of attacks that did actually work in practice. So what about the impact, right? So we wanted to demonstrate possible attacks as well, because when you send a security paper to security conferences, often they want to see real proof, right? Although you actually shown that you can inject packets and create errors, people say, yeah, but you don't demonstrate an attack. So we wanted to actually demonstrate real attacks as well. So we abused a chunk body parsing discrepancy between Akamai and Nginx, these two specific technologies. We configured Nginx to serve the OWASP multimedia. It's a framework of vulnerable web pages, right? And we showed scenarios where you can bypass headers, you can hijack requests, and we can even deliver attack payloads, for example, reflected cross-site scripting attack, right? So we set up our own environment and attacked it using HRS to demonstrate that some of these scenarios are not only possible, but they're realistic, right? So these attacks with these two real technologies did work, and we were able to confirm them. Also, we wanted to estimate server combinations, right? So one question is, okay, you have all these technologies out there, you looked at several of them, right? But are all technology combinations realistic with respect to HRS? For example, is combining Apache with Squid, is that a realistic combination in the real world, right? So maybe people never do that, right? Maybe there are 3 servers in the world who combine Apache with Squid, right? So we wanted to find that out. So we looked at the Tranco 10K list. So these are the most popular 10,000 websites on the internet. So we tried to figure out automatically what server combinations were being used in the wild, right? So we use fingerprinting for identifying technology combinations. Pretty much we were trying to identify what the proxy was using and what the origin server was using to try to see if that server combination we had determined before, or what server combinations were actually popular in practice, right? Is it, for example, is Nginx being used with Squid, for example? So we estimate that 17% of sites in the top 10K use a technology combination we have identified discrepancies for. This is a low estimate though, right? Because fingerprinting in practice is very difficult. So these are cases where we were able to fingerprint. doing this better is possible, something we're looking into right now, right? Which would also be pretty useful from a defense point of view. So this is a low estimate, but 17% is still very high, right? So for the discrepancies we found out automatically, close to 20%, I would say, are realistic combinations, which means that if I can take those results and if I can start attacking websites, those discrepancies that I discovered could actually be exploited in practice, right? There's a good chance of doing that in practice. So the fifth summary is body parsing discrepancies can be exploited for HRS only when certain conditions hold and certain technology combinations are also hold, right? So there might be discrepancies that I found out automatically, but they're never used in practice, right? Just because I find a discrepancy doesn't mean I'll be able to use this vulnerability. But you show that in many, many cases, if you're doing this randomly on the entire internet, you can find a lot of HRS vulnerabilities. So finding these results, we did a lot of disclosure. We contacted Apache Tomcat. They assigned a CVE. They confirmed some of our findings and said, okay, yeah, this is actually a problem. They fixed it. Nginx implemented hardening measures. So our students had contact with them. So, they took these very seriously and they changed some of their implementations based on our findings. ATS showed its willingness to add T-Reqs to their tool set. So they said, hey, we like this tool. We'd like to use this going forward to evaluate our own installations, right? Our own implementations to see if there are discrepancies, right? With other implementations. CloudFront discovered holes in their defenses that we reported to them. Akamai, where one of the lead authors was working at, coordinated a response with the co-authors, right, of this work. So they, of course, take it very seriously and they're very interested in this. So the question is, well, there is a lot more to explore, right? So non-standard HTTP headers, non-default configurations, higher number of mutations, you can do longer experiments. So if you are actually having malicious intentions, you could set up a framework like this and scan the internet, do much longer experiments, you could probably find much more things, right? This is still an issue. It's very difficult to fix, and people are finding more and more issues, and they're taking it more seriously, right? So interestingly, the question then becomes, okay, who's to blame, right? There are HTTP specifications. So why do you have this problem, right? So interestingly, we think nobody's here to blame because combinations of technologies create this issue, not the individual servers, right? It's not the case that Akamai is at fault. It's not the case that Apache is at fault because they have not implemented the HTTP specifications correctly. When you look at these servers individually, they're actually doing a good job, right? They're actually interpreting HTTP as they are supposed to interpret. But because the specifications are very difficult to write down in a lot of depth, and sometimes parts are missing, they're open to interpretation, maybe that's a mistake, right? People end up interpreting them differently, which leads to this issue, right? So the combination leads to these security problems and not the individual server, right? That's why it's also more challenging. And this has become more acute just because we have more CDNs on the internet, right? So, Akamai was around here in 2005, but not a lot of websites, not the majority of the websites were not being hosted by CDNs. Today we have cloud services, we have Akamai, we have Cloudflare, and organizations rarely host their own websites, right? They outsource it. Somebody else takes care of it because it makes it easy for you to deal with denial of service attacks, load management, and things like that, right? Security as well. Because we see more of that, it means that you have more of these technology combinations, right? You have your Apache server, and you're getting requests from some other third party, which can then lead to issues, right? So all of these things can become, lead to this problem. So there is an open research problem, of course. So this issue is something that's worth looking into. The reality is complicated, right? RFCs are ambiguous, bugs are inevitable. And if you say, okay, why is this happening? Like, why are they doing certain things the way they're doing it? Say a company like Akamai, they also have a lot of legacy code. They have a lot of clients. And often when you say, why don't you just fix it? The answer is, well, we can't, right? Because there are a lot of real world constraints, right? So they might do, HTTP request rewriting, and they've been doing it for a long time. And it's not that easy. And a lot of things are being done for performance reasons as well, right? So if you say, why don't you, break the connection every time a request is sent, right? Well, if you do that, then it leads to big performance issues. So you can't do that as well. So this ends up being quite problematic. So in any case, this complex ecosystem, predicting, detecting, mitigating, or fixing HRS is a non-trivial and interesting research problem, right? If you're interested in this area, I think there are more things that can be done. One thing we're looking at right now, sort of completed, evaluating it, is fingerprinting. So like fingerprinting requests automatically, right? If you're able to do this well, then you can find out what technology combination you use, right? That's valid. We looked at HTTP 2.0, for example, right? We're looking at other things as well, trying to, figure these things out automatically. And companies like Akamai, I can tell you, if you can come with a solution and say, look, this actually fixes the HRS problem, or we have these tools that really help you, they would be very, very interested. So there's actually a big demand right now. So it's actually an interesting area. So to conclude, we developed an HTTP fuzzer to look at this problem more systematically, to look at different HRS attack vectors. We designed an experimental setup for more complete and effective testing than previous work. People have found these things manually, but we wanted to actually explore what's happening on the internet automatically, doing measurements, and coming up with some automated tools that allow us to do that. We provided insights into conditions for discrepancies to be used for HRS. We looked at what technology combinations are actually more realistic, for example. And we showed the possibility of HRS attacks on popular servers today. And even today, people are finding these quite often, right? So it's not a solved problem. And this will continue to be so going forward, just because CDNs are actually not going to disappear anytime soon, right? So the work led to real-world discoveries of problems and their fixes. So that actually made us quite happy. That's why I like this work. I think the students enjoyed it as well, because they did something which led to a good paper, but also some good results and impact in the real world, right? So that work has actually continued. So with that, thanks very much. If you have any questions, I'm happy to try to answer.
I personally enjoyed it a lot. So I have two questions, but I'll let the students ask first. Any questions?
Yeah.
Hi, my name is William, and I work on autonomous vehicles. So as you probably know, most of the vehicles right now, they're connected either via a 4G chip that the OEM installs in their vehicle. So that I don't know what protocols they send the message through, probably still HTTP. So that would an attack with HRS be possible?
An issue, yeah. It's a very interesting question. So I don't know what protocols they're using. If they're using HTTP, an attack would work if requests are being forwarded and if there's some sort of a server, right? I don't know how these protocols work, but if you're receiving requests in HTTP and you process it in some way, and then you forward it to some other component that has another HTTP part, it could lead to smuggling. I'm not sure what the impact would be. It's possible. Conceptually speaking, these types of issues in security have been around for a while, right? So for example, for firewalls, they've been fragmentation attacks, right? The very old attack where you used to send, IP packets, they get fragmented, which means you bypass the firewall, and then at some point they get, defragmented, and then that packet is forwarded, so the firewall never sees it, right? So basically, you have two technologies dealing with it in two different ways. So, conceptually speaking, I can imagine there are other implementations where you would end up having issues, but I can't say what the impact would be.
Okay, yeah, thank you.
Yeah, I have a question.
Yeah.
So, what does the attacker needs to do to perform the HRS?
First, you need to discover some header combination or some request that your target server, target technology, accepts, although you're actually injecting another packet, and the target server, say Apache, forwards it to the other target destination. So it has to be some sort of forwarding. So suppose that you discover that Squid has this issue, right? And say University of Delaware is using Squid, right? And you're attacking, say, Northeastern because packets are being sent to Northeastern, right? So you would first send the packet to Squid, add this extra malicious request, which would then be forwarded to Northeastern, and Northeastern would ignore the first part, but would take the malicious part and do something with it. So basically, there has to be some sort of forwarding, and both of these servers need to deal with it in different ways so that you're actually able to smuggle these things. There are some examples in the paper as well. And if you actually Google around, people have actually implemented some demos and things like that.
So I have two questions.
Yes.
First one is about the details. So generally, when we talk about fuzzing, for example, fuzzing the OS, we use the code coverage information to guide the mutation. So in your system, is that kind of similar mechanism, or you just do the right mutation?
Yeah, excellent question. So we went for the low-hanging fruit. So in this case, there's no code coverage because this is black box, right? So we're not seeing the implementations. Using that on the web application code could be an interesting direction to take, right? So that will be something to explore as well. So you could do the fuzzing better. For the low-hanging fruit that we did in this case, right, it led to pretty good results because, you know, there were so many discrepancies, but you're right, you could find even more. So which means that finding the attack should not be a problem. You could do even better probably.
Thank you. Another question is more about high level general question. So as a cybersecurity researcher, I know that the inconsistency between different implementations among different parties exists and probably will be here forever.
Exactly. Yeah.
It's super difficult to fix them because you have to coordinate among different parties.
Yeah.
Sometimes they just don't fix it and they don't know how to fix it. So as a cybersecurity researcher, what can we do beyond just discover those vulnerabilities?
Yeah, great question, right? So, okay, you could do this forever, right? So, you know, if you write another paper where you find 200 more, at some point people will say, okay, you know, you're always doing the same thing, you're finding more bugs, so why would we accept this paper, right? I think an interesting direction could be looking at the HTTP specifications, for example, maybe using formal methods, right? So is there a way to compare the specification to the implementation automatically? So, you know, if you can actually take a software and maybe figure out automatically the model of how it's implementing something and compare it to the HTTP specification, then you could start comparing different implementations to see where they differ. And maybe you fix it so that everything becomes standard, right? Or maybe you analyze a protocol automatically and figure out where there's room for interpretation and you try to close those gaps, right? Or maybe you set up something like this as a part of your development process where before you deploy, you know, you press a button and all these fuzzing is done so that you find all these discrepancies before the software is shipped out, right? So I see different venues for exploration, but in practice, they're probably challenging, right? It's not easy to look at the spec and get a model out of it or something.
Any other questions? So if no question, thank you again.
Thank you.